Okay, let's talk about some basic principles of our power system. So I believe most of the materials I'm going to cover today or by this session, not that unfamiliar to you because you may have learned those material from a 325 or from a circuit system, other courses on the circuits. But today I'm going to use some conventional definition and languages only for power system. Okay, we'll start from a very simple circuit because this course is going to focus on AC power systems. Let's just think about the simplest AC power system or AC systems, which is a circuit, a single source and a single load connected by wires or transmission lines. And for the source, I put the positive sign there, which indicate that's a polarity of the source. Because it is AC source, so it doesn't mean the potential of that end is always higher than the other end. It only just means if I want to use this function to categorize the voltage of the source, this voltage is measured as the difference of a potential between the positive terminal relative to the other terminal. No, that's only what this plus sign mean. And the current is another function leaving from the positive terminal. So when we call one equipment as source, we mean there's some current leaving from the positive terminal. But whether that source really behave as a source, that depends. So later we'll show some examples. Even we call the left circle as source, but it doesn't behave really like a source because it might be a pump storage hydropower plant, right? So working at in the motor mode. If it's working in the motor mode, it's really a load. But when we model the system, we just define the polarity. We just put the positive sign here, and such as we can give it a function for the voltage and give another function as a current from this equipment. And let's just call it a source temporarily. So we'll have a instantaneous voltage and instantaneous current. Just to make it simple, we just assume both instantaneous values follow a cosine function. So and with the same frequency, omega. But they may have different phases. So for voltage, we use theta V, and for current, we use theta I. And the other equipment, we'll just call it a load. So usually load means the current will come into the terminal, which has the positive sign there. Positive sign means it's just matching the positive sign of the source on the same side. So current coming into the positive terminal, that equipment will be treated as load. Similarly, so whether that device really behave like a load, we don't know. We still need to do some calculation because if it is a battery under charging condition, it can be a load. But if a discharging condition, it will be a source. Since this course focuses on steady state analysis, so in steady state analysis, we treat all those colored parameters or variable as constant. So which include first the frequency will be constant. So here we use omega, which is 2 pi times f. F is the frequency. In the US, that will be the 60 hertz. And 2 pi times f will be 2 pi times 60 hertz, which is about 377 reading per second. So which is accurate enough for calculation. Corresponding to 60 hertz. And the two angles are also constant. So which means their difference will stay the same under the entire steady state analysis. And the peak values of two cosine function will be constant. The unit will be a volt or ampere. Usually we don't use peak value for calculation. We are more interested in the RMS value, which means the root mean square value. The root mean square value simply just peak value divided by root of 2. So why do we need RMS value? Because it's more convenient to tell you the equivalent DC voltage current consuming or generating the same amount of energy and power. For instance, if you want to calculate the energy consumed by this load, if it's a resistive load, it can be simply modeled by a resistor, R. And if we calculate the total energy consumed by the load by 1 cycle, 1 over F, then we divide the energy by T. Capital T will calculate the average power. So if we do such calculation, and we'll do the integral of the instantaneous current square multiplied by R and do the integration for 1 cycle. And this is the energy consumed by 1 cycle. And we plug in the instantaneous current. It will be this cosine function. So Im is constant, so we'll move this one outside. And here, we want to integrate this cosine function square. We can use this formula to convert any cosine function square into a half of 1 plus the cosine function with angle doubled. Okay, we can use this trigonometric identity, and then we integrate 2 terms. If we integrate this one, that's simply just a capital T and divided by 2. And if we integrate the second term, the second is a periodic function with double frequency, but we only integrate for 1 cycle. Oh, sorry, double frequency, we integrate for 1 cycle, and the double frequency has half cycle, half T at the cycle. So which means the integration has to be 0, right? So if you integrate any periodical function for the period, or maybe a times of the period, so that will be always 0. So the second one will be 0. So finally, you only have a capital T as a result of integral. So this will be the result. And you want to put these 2 inside of the squared. So you have this current square multiplied by RT. This is like a DC current. So now you understand why we're interested in the RMS value, because that is equal to the equivalent DC current. And similarly, we'll use also RMS value for voltage for the calculation. Next, we want to introduce the concept of a phasor. Phasor may mean different things, maybe a vector, maybe some things revolving, but in power system, we especially mean just a simplified notation for a sinusoidal waveform. A phasor maps the sinusoid waveform to a single complex number that only carry the amplitude and phase. And we ignore how it really varies in time in detail. So for instance, if you have a sinusoid waveform moving, changing with time, and if we observe the amplitude will stay the same, and the value will be changing between positive and negative amplitude. And this trajectory is exactly the projection of one point moving along a circle at a constant speed. So this constant speed will be the angular frequency of that sinusoid waveform. Which means if we have this function indicating a sinusoid waveform, to categorize this waveform, we need to write the peak value, the cosine function, the phase, and frequency, and also its function of time. So instead of writing out the entire expression, we only just need to capture the peak value and also the phasing. And we assume the omega will be same, because to power system, if we assume a simultaneous frequency, which is 60 Hertz, that will be almost everywhere. Definitely in the dynamic analysis, the frequency itself may change by maybe 1 or 2%. But in steady state analysis, usually frequency is constant. So which means here only 2 pieces of information really important to us, which is the peak value and this angle, right? We don't have to write that cosine function in every expression. Then we can just use a complex number with this peak value and angle to correspond to this waveform. And this is very convenient because if you have a 3 waveform, they all are synchronized at the same frequency. Maybe one indicate a current, the other two maybe indicate the voltage. So to do such calculation, we rather use either we use the all 3 waveform in all expression, or we just treat each waveform as a complex number. So they're actually revolving at the same speed along 3 different circles. And you can tell if they keep the same the angle unchanged. So they will form a parallelogram revolving together. Okay, so we just take one snapshot. We don't really worry about the starting phase. We just capture their peak value, their angle at a certain snapshot. Then we can capture the relationship. So we can define phasors for such a waveform. Just, so for the first case, we only just use this simple complex number to categorize this one. We don't worry about what is the starting time, but we just put the angle there. As long as all the waveform are relative to the same starting time, and they will keep the relative position all the time. So for the second case, we'll have 3 complex number to calculate if we have the first one plus the second one, that will be the third one. So that one can be simply calculated using the complex numbers, so addition of complex number, instead of adding the first waveform and second waveform point by point to get the third one. Okay, so now we're ready to define a phasor for power system. We assume a steady state condition with constant frequency omega. We define RMS phasor, so not peak phasor, because I said, so we have a peak value and the phasing angle which are really important. But for the convenience of calculation of power, we usually the RMS value of voltage currents are more useful than peak value. So we define RMS phasor, which means we'll keep the angle of voltage current and also the RMS value of voltage and current. So we start from an instantaneous voltage. Here we only, so the peak value, angle, those two are actually the most critical information. And we first just get the RMS value. So we will keep the RMS value and the angle, and then we form a complex number. The complex number will be, we call it capital V and capital I. So we know both V and I are complex number. So their absolute value or magnitude will be the RMS value of the voltage. And they also have angle, theta V, theta I. For complex number, there are several ways for the notations. So either we put absolute value together with angle. This is the conventional phasor form. Or you can write it in such a way with absolute value and multiply by a exponential function of the imaginary sign times the angle. So either way will be fine for complex number. But usually in power system for calculation, we can use this one, the phasor representation. And compared to the previous slides, we know that we define reference frame revolving at omega. Angular frequency and voltage occurring in both sinusoidal waveform changing at the frequency of omega. So the V and I as the two phasors will be revolving together with reference frame. And the voltage relative to reference will be the angle theta V, and I will relative to reference as theta I. And if they maintain the theta V, theta I constant, so their difference has to be constant. So they will have a constant angle difference between the two phasors. We don't really worry about where this reference is because it's not important. Because later, when we calculate the power doesn't need to know where this reference. So rather, this angle difference is really the important information we want to know. Okay, so in such case, we call the voltage phasor is leading current phasor by theta. Or you can say current phasor is leading voltage phasor by 360 degree minus theta. So either way is fine, because you can treat this voltage ahead of current or current ahead of voltage by 360 degree minus theta angle. So with respect to a reference, a phasor carries amplitude and phase angle information of a time domain sinusoid waveform of a common frequency, mapping a time domain signal to a complex number, such as we can define such a phasor for every sinusoidal waveform. And then in the calculation, instead of do everything in the time domain, to calculate, for instance, like one form added to another form, one waveform multiplied by another waveform. So you will involve a lot of addition, multiplication of a sine, cosine function. That will be very complicated. But now we have a complex number for each sinusoidal waveform. So we only just need to know how to do the operation of a complex number. So that will be much easier. If that sounds, but that's definitely you have to know how to do the operations of a complex number. If you know it, that will be very simple. So instantaneous voltage will be replaced by a complex number with magnitude and angle. It also has real part, imaginary part. So you can choose either use this way, phasor representation, or real part plus imaginary part representation for calculation. Either way, depending on which is similar to you. So usually do any multiplication or addition, the phasor representation is easier. But if you do any addition, subtraction, the second one is easier. So similarly, we have a current also represented by a complex number. Okay, so next, let's talk about load. We define load impedance. Load impedance is just a concept integrating the resistance or inductance or capacitance into a single complex number. So we just define load impedance as a single complex number that is defined as the voltage phasor divided by the current phasor. So Z has real part, definitely, because it's also a complex number, has real part, which is resistance, imaginary part, which is reactance. And so that's a real part plus imaginary part representation. But by definition, it's just a division of the voltage phasor by current, because both V and I are complex number. So the result will be the division of the absolute values, the RMS value, and also theta. So theta here is just difference between the voltage angle and the current angle. So from here, you know that's basically just the difference between the two angles. Okay, so that's the definition of load impedance. So you know the load impedance really tell how you change from a current phasor to voltage phasor. Okay, so first you need to amplify the magnitude by this value, by this ratio. Then you need to increase angle by theta. Okay, so you make this current be longer by this absolute value. And then you add another angle by theta. So that's what it means. So rigorously speaking, the Z here is a complex number, but it's not a phasor. Z is not a phasor, but it's a complex number. Why? Because they represent the rotational transformation from current to voltage. So if we treat the voltage as a phasor or something like vector, so in the complex domain, so it has a real part, imaginary part. Current also is a vector. So what Z is doing really just a transformation of the current vector to the voltage vector. So Z actually is a matrix. Okay. So in power system, because we define any phasor which correspond to some sinusoidal waveform. So we can call voltage, current as phasors, but impedance is still treated as a complex number by itself. Is not a phasor. So my suggestion is not calling impedance as phasor. Any question? Okay. Let's move on. I assume everybody know how to do operations of a complex number. I just quickly put useful formula into these slides. So complex number, assume there's an imaginary unit, which is just the square root of -1. So if Z is a number, if it's complex, it will have an absolute value and angle theta. For real number, theta will be 0. If theta is not 0, it will have real part, imaginary part. And if we keep the same real part but opposite imaginary part, it will get an image relative to the real axis. So that is called the conjugate. Okay. So if Z is a complex number, Z star will be the conjugated Z. It's symmetric about the real axis. And if Z has theta angle, the Z star will have negative theta. So if we know the Z and Z star, we can calculate the real value and also the imaginary value. So absolute Z and absolute Z star are same. Based on the Pythagorean theorem, you can easily, if you know the real part, imaginary part, or you know the Z and Z star, you can calculate the absolute Z. If you want to do any operation, which is one of addition, subtraction, multiplication, or division, so you can choose either do the operation first, then find the conjugated value, or you find the conjugate of each one, then you do the operation. That's it. If you have two complex values, the multiplication of the two complex value will be equal to a number with the magnitude, which is the multiplication of the two magnitude of the complex value and also the total angle. This is easier. So when you do multiplication, this formula is the easiest way to do the multiplication, because later we'll do some like calculation for power. If you have voltage, current, you always need to do multiplication. So usually change voltage current to the phasor representation with absolute value and angle. So this is easier. So if you really want to know the real and imaginary part, you can use this formula. That can be easily proved. Usually I don't remember this one. For the division, if you want to calculate the impedance, if you know the voltage divided by some current, so the answer will be the absolute value will be that just the division of the two absolute value, and angle will be the difference of angle. Definitely, if you really want to memorize this one, that's fine. That's this formula. Okay, now let's come back to our simple circuit, because we are going to define the power, because power will be multiplication of a voltage and current. So we start from an instantaneous voltage and the current. We'll have to give it an accurate definition of a power. We need to multiply the voltage by current point by point along the time frame. So we are going to figure out what this power is as function of time. So here we assume the angle, the theta will be the how much by which the voltage is leading the current phasor. Okay, so usually we know if the voltage is leading the current, which means this load is somehow inductive. Inductive means it has some maybe resistance and also has some inductance inside. Or it may have a number of inductances and a number of capacitances, but the overall inductors are more than the capacitors. So overall behave like inductive. So that will make the voltage be somehow leading the current from the outside. if we have a negative theta, which means the load is a capacity, which means the total capacitance inside the load is higher than the inductance. So we directly define the multiplication of the voltage and current waveforms, point by point, at each time point of time as a time function pt. That is the instantaneous power. So that's the definition of instantaneous power. So next, we just need to figure out a more useful formula to calculate the instantaneous power. Here, we need to deal with this multiplication of two cosine functions. So we know if we calculate cosine alpha times cosine beta, that will be half of two items. The first item is cosine of angle, which is the difference. The second is the total angle. Okay, we're going to use this identity to simplify the formula. So we have half of the multiplication of the two peak value, and here we have cosine angle difference and cosine the sum of the angle. So the first item actually cancel omega t. That gave you something doesn't depend on, not depending on time. So next we want to deal with this one. Okay. So here we can use another formula. First, let's just let's just get rid of the theta I. Okay, because we know the we have three angles. We have a theta v, theta I, and this one is actually theta. So we only have like we can keep theta and theta v. So we just replace theta I by a theta v minus theta. We'll have this expression. Then we're going to use this another trigonometric identity. So it is about the cosine, the difference between two angles, so which is equal to the two items. The summation of two items. First is the product, and second is of cosine function, and second is a product of the corresponding sine functions. Okay, so here what we do is the first item will be cosine this angle multiplied by cosine of this angle, and plus, because here you notice the sign is a change from negative to positive. So if here is negative, here will be positive. So it will be a product of two sine functions of the first angle and the second angle. Move on. So we will have okay. So for the first item, we'll move a cosine theta out here, and inside will be 1 plus cosine 2 omega t plus theta v. Okay, and the second item move here, and also we want to change the peak value to the RMS value. So actually, we change the half into the product of the 2 1 over square root of 2. Gave it to each of the peak voltage and peak current. So we have RMS value here. So this one looks very complex. I'm not going to ask you to memorize this formula, but it's very useful to understand what's happening when the load is not purely resistive. It has when the load make the angle between the voltage current be not the same. So the instantaneous power will follow this complex function. Let's just give the first item a name. We call it PR. The second function is PX. So let's just take a look at what happened with those two functions. Instead of finding the general property, maybe it's easier just to give it some value, right? So we use one example from the textbook. So let's assume the instantaneous voltage will be this one, have 100 volt as peak value, and the phase angle is simply just 0. And we have load impedance. We're going to determine the current and also instantaneous power. So voltage, we first change voltage to the Phasor value. So 100 divided by root of 2 will be the RMS value, and theta V here will be 0. Current will be simply just voltage divided by Z. So it will give you the RMS value, and the angle will be negative 60 degrees. So the current will be lagging the voltage by 60 degrees. So if you have to draw something like this one, assume this is V with 0 angle, and current is about 80% of the length. This is too small. 60 degree will be something like this one. Right? This is negative 60 degree or positive 60 degrees. So which means the theta, how much of voltage leading the current. So the waveform of current will be this one. We'll have 80 as a peak value and a negative 60 degree at the phase. So we plug in all the expressions into the formula we derived from the previous slides for the instantaneous power. We'll have two items, both just function of time. The first one is based on cosine function, second based on sine function. And I color the peak value of both functions in green and blue because those really indicate some very useful physical quantities. The first one will be the PS, PR, second will PS. Okay, so we're going to draw a number of waveforms. So in the first waveform, we'll draw the voltage and the current. Because here we use cosine functions for the sinusoidal waveform. So voltage will start from peak value 100. After 360 degrees, it will finish one cycle. And current will have the same period, but it will start at negative 60 degrees. So current will reach the peak value at 60 degrees, so which is lagging the voltage by 60 degrees, but also finish the one cycle to reach the same initial value, okay? Second plot is just you multiply the two waveform point by point for each time. For instance, 100 multiplied by this value will give you this value. So just do that, okay? For every time point, you get the second waveform. Yeah, so that's actually what this instantaneous power means. If you take a look at this waveform, it's still sinusoidal waveform, but the period become half. So for 360 degrees, for voltage current to finish one cycle, and for the same range, the instantaneous power will finish two cycles, right? So they start from here, and here is finish first cycle and finish second cycle. So instantaneous power will change faster, twice as fast as the instantaneous voltage current. But that actually can be taught from the frequency here, because the instantaneous power is based on two also periodic function and at double frequency of voltage and current. And if we draw the PR and the PS, which are the first and second items of the instant power, which will be those two plots. PR will be also like sinusoidal waveform at twice of the frequency, which means you finish two cycle within the one cycle of voltage or current, and the entire waveform is above 0. Okay, it's a non-negative, because the cosine function will be changing from -1 to +1. So then you add the +1. So this entire waveform will be above 0. Okay, so what is the 200? Why, sorry, 2000? Why is that number important? Because that 2000 is actually the average value of this waveform. Which means if you integrate the area under the green waveform, so that is actually this area, this rectangular area. That's the total energy, the load consumed over one cycle. Okay. Second item, That's a blue waveform. That's also sinusoid, but it will be the mean value will be 0, which means if you integrate the area under the blue waveform, that's 0. That's nothing. Okay, so finally, this rectangular area indicates how much energy the load will consume for 1 cycle. So if you divide this area by time, that will tell you the average power. So if you treat this load as some purely resistive device, so this is really the total energy the device consumes. So that's why this number is very important. They really tell you the average power of the device. And the other number, 3,464, is also important because it tells why this device is different from purely resistive load. Okay. So if this blue line is exactly 0, which means this is more likely just purely resistive load, and this green line will be also a straight line of 2000. But now the green line is actually changing the sinusoid waveform, and blue line also in another sinusoid waveform. That means this load is somehow either inductive or capacitive, but that's not purely resistive. So this blue line really tells it's not a purely resistive load. Okay. So the observation, so, PR and PS and also instantaneous power change as twice as often as V and I, and PR is always a non-negative, which means either 0 or positive. The average value 2000, and PS is considered to be the power exchange between the source and load, because for some time it's positive, which means it's consuming some power from the source, but for the next maybe half cycle, it will become negative. It will give exactly same amount of energy back to the source. So if you integrate this area and that area, that's exactly the same. So you just temporarily consume some power, but then we'll give power back. Okay, so the blue waveform, the PX, actually indicates certain pattern, how this load is exchange energy with the source, but the average is 0. Okay, yes, let's maybe finish this one. Okay, so next we can we'll define first we calculate the product of the two absolute value of V and I, the RMS value. So we call this one as apparent power. So that's actually indicate the maximal instantaneous power the system may have. So the unit will be we call it volt ampere, because we're not sure that is really the power causing the energy assumption or maybe certain pattern of a power exchange. Usually the unit will be VA. And we call the we calculate the product of the RMS value of voltage, current, and the cosine theta as the active power. So this one really indicate the real and active power, or the average power, because this corresponds to this one. So this is the 2000, if you remember from the previous example. So this is like 3, 4, 6 fourths, another number. So that 2000, which is the rectangular area divided by time. So that part is correspond to we call it P, which is really the real power, active power. This is really the power the load consume. So the unit will be the same as conventional power, watt or W. And we call this cosine theta, which is the apparent power multiplied by the cosine theta. The theta here is the difference between the voltage and current. We call this power factor, because that means percentage of the apparent power really become the real or active power. So if a theta is positive, we call it a lagging power factor because the current is a lagging voltage. If theta is a negative, current will be leading the voltage. We call it the leading power factor. That will be the case. Leading power factor if theta is negative. Because theta here is just means by which the current phasor is lagging the voltage. Then for that, the other number, so which indicate how the load is exchange energy with the source. That one is defined as the Q. We call it reactive power. Reactive means it's not real power, but it's indicate how this load behave differently from a purely resistive load. So for the unit, we cannot use the watt because it doesn't mean real power, but it's still the voltage multiplied by current. So we just call it volt ampere reactive, or VAR capital, or VAR only lower R, or maybe only capital V, either one, anyone. So you may see anyone appearing in the literature. But usually, if you are not sure which is better, just keep using everything capital.